This is video lesson number 8 in our chemistry series. We have an introduction to chemical reactions and counting atoms and balancing reaction equations. So I apologize in advance, this is going to be a bit of a long one, but there will be a break in the middle where I will suggest that you pause the video and do a few practice questions before continuing on. So chemical reactions. There's a few different properties and characteristics of chemical reactions, so we're going to go through those first. First of all, chemical reactions involve a chemical change. So those chemical changes that we were talking about in our very first lesson, we're going to be seeing those types of things. So a change in temperature, a change in odor, a change in color, gas being formed, or precipitate being formed. They also occur at different rates. So a rate is something that's measured per time. So some reactions happen very quickly and some happen much more slowly. So an example of this would be iron rusting is a very slow reaction versus if you were to make a volcano project where you mix baking soda and vinegar. It happens very quickly in a matter of seconds. So chemical reactions are used to create new substances with useful properties. So things like aspirin is something that you make with a chemical reaction. It's an organic synthesis reaction where you're bringing two compounds together to create the molecule aspirin, which is a painkiller. Okay, chemical reactions either consume or release energy, and this is usually in the form of temperature. So either they consume energy in the form of heat and so they feel cold to the touch, or they release energy in the form of heat so they feel hot to the touch. They can also release light as a source of energy as well in some reactions. Okay, chemical reactions involve a rearrangement of atoms. So you have your reactants, which are your starting materials, and they contain specific atoms. And then when the reaction happens, those atoms get rearranged into different groups, forming new compounds and new things. Okay, chemical reactions all obey the law of conservation of mass. So the law of conservation of mass. Okay, and what this means is that we cannot create or destroy matter. So anything that you start with needs to be produced at the end. We can't have it just disappear and go into nothingness or create something out of nothing. So, which states that matter cannot be created or destroyed. Therefore, in a reaction, the mass of the reactants must equal the mass of the products. Okay, or the number of atoms that you start with in the reactants must equal the number of atoms that you end with in the products. So to add a quick definition here, reactants are your starting substances. And your products are your ending substances, so they're what you make. Now there are three types of equations that we use, and those are word equations, which use the name of your different compounds. And then there are skeleton equations, which use the formula, so it's like a shortened version. But a skeleton equation isn't fully correct until it's balanced. So then we also have balanced equations as sort of our final type. Really, skeleton equations are just a stepping stone to getting to a balanced reaction equation. So we're going to look at an example that's drawn as molecules down here at the bottom. Okay, in this example, we have a hydrogen gas molecule, so that's 2 hydrogens stuck together, plus another 2 hydrogens stuck together, plus an oxygen molecule, which is 2 oxygens stuck together. And so these are all the atoms that we have to work with. We have 4 hydrogens and 2 oxygens. And they're going to rearrange. The arrow in a reaction indicates the chemical change. And so the atoms are rearranged into 2 water molecules with an oxygen and 2 hydrogens stuck together. So the word equation for this reaction is going to be oxygen plus hydrogen forming water. Now you could call water oxygen or dihydrogen monoxide if you would like to, but you don't have to. Water is perfectly acceptable. So we have oxygen plus hydrogen making water. So our word equation just has the names of the compounds involved. The skeleton equation is the sort of lowest, simplest ratio looking at the formulas. So oxygen is O2, hydrogen is H2, and then we show our chemical change with an arrow, and we're forming water, H2O. Now, oxygen and hydrogen come from a special group called the diatomic gases. So diatomic gases, we have a little acronym that we use to help us remember which ones those are. In general, most elements, when they're on their own in a reaction, so just in elemental form, they don't come in pairs. They come as single atoms rather than 2 stuck together. But the diatomic gases, we use the memory trick Hofbrinkel to help us remember which ones need the 2. So all of these elements, hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine, when they're in a reaction like this and they're on their own as an elemental form, okay, they come as 2 of that atom type stuck together, like you see in the diagrams here. So you probably have heard of oxygen gas being O2 before, and there are a number of elements that are like that. So this is the little list of the ones that get the little 2 as a subscript to show that it's 2 atoms stuck together. So here's our skeleton equation, 2 oxygens, 2 hydrogens making water. Now you might be able to see that that doesn't match what's down here. Down here we have 2 hydrogen molecules and we have 2 water molecules. And that's because this is showing the balanced reaction equation. Here, if you count out the atoms, we have 2 oxygens on this side and 2 hydrogens on the side. Here we have 2 hydrogens, which matches, but only 1 oxygen. So we have an extra oxygen on the reactant side, and we need to make sure that it's balanced so that it follows the law of conservation of mass. We have to have the same number of each element type on both sides of the arrow. So to balance this reaction, we have O2 plus H2. We're going to rewrite the skeleton equation, makes H2O, but now we see we have 2 oxygens here, which means we need 2 on that side. So we can add what are called coefficients. Coefficients are big numbers that go in front of the compound, coefficients. And it basically tells us that we have 2 of that molecule type. So in this example, we have 2 water molecules. So when you're counting out the atoms now, You have to, anything that follows the coefficient has to be affected by it, which means that we now have 2 times 2 hydrogen atoms. So here, 1, 2, 3, we now have 4 hydrogen atoms, and this 2 applies to that one, 1, 2 oxygens. So on this side, 2 oxygens, on this side, 1, 2, 2 oxygens. It's good. But the hydrogens, we've got 4 on this side now, which means we need 4 on the reactant side of the arrow. And the diagram shows us how we do that. So 1, 2, 3, 4, there they are. We need 2 molecules of hydrogen. So we're going to add another coefficient in front of the hydrogen gas to tell us that we have 2 of those hydrogen molecules. So these double H molecules, so 1 and 2 of them. And now we can see that we have the same number of each element type on both sides. So there are some rules that we follow for balancing reaction equations to help keep it a little bit easier. We need to be able to count the number of atoms in any one compound and on each side of the arrow. So you'll see there's a whole bunch of practice here, which we'll get to in a minute. But basically we need to balance reaction equations by counting out the number of each atom type on both sides of the arrow and then making sure that they end up the same amount. So rules for counting atoms. Okay, the first one is that a subscript, so a subscript is like a lowercase thing that's down below, okay, tells you, a subscript tells you the number of atoms of that element in a molecule. So if we look at this example, this 3 down here tells me I have 3 hydrogens in this molecule. The 3 only applies to what is directly beside it. It does not affect the nitrogen, only the hydrogen, which is right beside. The second rule is that the number in front of the chemical formula okay, that's what we called the coefficients. Okay, so in this example, that would be something like this big 2 out in front here. So that number tells us, tells you the number of molecules with that formula or of that type of compound. So in our example, this 2 in front of NH3 tells me I have 2 whole molecules of NH3. So finally, to get the number of atoms in a chemical formula or a chemical equation, okay, you have to multiply the subscript, so in rule A, and the coefficient, so from rule B. So the subscript and the coefficient together. So I'll do a couple examples here. Let's go through this first one that's already done for you. Here on the, so you can kind of even like think about it like this. This is your reactant side, this is your product side. On the reactant side, I have 2 as a subscript for this N, and you'll notice there's no number in front of it, And what that means is there's an imaginary 1 there. So if a coefficient is a 1, we just don't write it. It means there's just one of that particular molecule type, but we don't actually write it there. But you can think of it as 1, so we can get the coefficient, times the subscript. So 1 times 2 is 2. That gives me 2 nitrogens on the reactant side. For the product side, here we have 2 times, now you'll see there's no number on this as a subscript for N here, and that's because it's an imaginary 1. So we talked a little bit about that in some previous lessons, but we don't write the 1 if it's just 1, but you can think of it in your brain in terms of multiplying the subscript and the coefficient together. 2 times the subscript is 1, gives us 2, so we have 2 on the product side as well. So this has equal numbers of nitrogen atoms on both sides of the arrow. The hydrogen, we have 3 molecules of H2, where you have 2 hydrogen atoms stuck together. So the coefficient times the subscript is 3 times 2, which gives us 6 hydrogen atoms on the reactant side. On the product side, we have 2 times subscript here is 3, so 2 times 3 is also 6 on the product side. So here you can see when these are equal, that this reaction is properly balanced. It has equal numbers of each atom type on both sides of the arrow. So what you're going to do is you can pause the video for a few minutes and go through and practice counting atoms. So each one you'll go through and count them out and then determine which ones are balanced and which ones are not. So not all of these reactions have been balanced correctly, okay? But you can go through, check them all, and identify which ones are not balanced and which ones are. Okay, the answers to that page will be posted in the answers folder so you can check your work. On page 24, there's some more practice with some counting atoms and some naming compounds again, just to keep that fresh. So again, you can keep the video paused and go through and do some of these practice questions. The answers to page 24 are in the folder and you can check your work before moving on. Okay, so if you're gonna do that now. Pause the video before you come back for the second half of this one. So moving on, hopefully you're feeling fairly confident in counting atoms because we're gonna need that for actually balancing reaction equations. So now that we've talked about how do we count atoms, and we know that we need to have equal numbers of atoms of each type on both sides of the arrow, we're gonna go through the steps on how to balance a reaction equation. So here we have an example where we're looking at the reaction of aluminum and chlorine gas. So chlorine was part of that Hofbrinkel group, so we got that little subscript too. But any element that's not in that list, so Hofbrinkel, I'll write it out again in case we need it later, okay, would just be an imaginary 1 there. Okay, they're just on their own. And this forms the ionic compound aluminum chloride. To get this formula, you would crisscross the charges like you do normally with ionic compounds. So we want to start with our skeleton equation here, and we're going to count the number of atoms on both sides of the arrow and then figure out how we need to balance it. So to start off here on the reactant side, we have 1 aluminum atom, so you can think of this as 1 times 1. So 1 aluminum, and chlorine is 1 molecule of chlorine, which contains 2 atoms. So we have a total of 2 chlorine atoms on the reactant side. On the products side, we have 3 chlorine atoms and 1 aluminum. So here, 1 and 3. So that's the first step, is figuring out what you have, what's already balanced and what's not balanced. So when we look at this, we'll see that aluminum has equal numbers on both sides of the arrow, so it's kind of fine already. But the chlorine has 2 atoms on this side and 3 atoms on the other side, and we can't just pull 1 chlorine atom out of thin air and like into existence. We can't do that. We have to have equal numbers on both sides. So we're going to balance the chlorine, okay, by adding a 3 in front of the aluminum, or of the chlorine gas, so a 3 there, and a 2 in front of the aluminum chloride. So you can kind of think of this, it reminds me a lot of finding lowest common denominator in math. But whenever you have 2 and 3 of something, the lowest possible common number that you can make that is going to be 6. So anytime you have 2 and 3 on opposite sides of the arrow, make them both 6. So we do that by adding coefficients. A 3 here, 3 times 2 gives us 6 chlorine atoms on the reactant side, and 2 times 3 again gives us 6 on the product side. So now my chlorine is correctly balanced. But having done that, I have also affected the number of aluminum atoms. So now I have 1 aluminum on this side still, but I have 2 times 1 aluminum atoms on the product side. So now my aluminum isn't balanced anymore. So I need to go back and fix that. We want to keep the chlorine atom balanced, but to fix the aluminum, we can add the coefficient of 2 in front of the aluminum. So we already had the 3 and the 2 here, so 6 and 6 for chlorine. So that one was good. And now aluminum, 2 on that side, we add the coefficient 2 on this side, 2 and 2 gives us 2 and 2 aluminums on each side there. So when you're going through this, you can follow the steps here. Okay, you're going to write down the skeleton equation, okay, which is what we did at the very top here. Okay, count out the number of atoms on both sides of the arrow, and then multiply the compounds by coefficients that you can add in front to get an equal number of atoms on both sides. We'll do a few more practice questions together. People who like puzzles and stuff like that generally find this fairly easy, but it can also be very, very challenging sometimes. So as long as you sort of have a system and you keep yourself really well organized, you'll be fine. But it does take practice, and the more you do it, the faster you'll get at it. So here we go. So a general order for balancing equations is listed here. It's helpful to follow these steps, especially for reactions that are very difficult to balance. So you may find that you come across one that's really hard and you can't quite figure it out. Then you want to make sure you follow those steps properly. Some equations, you'll look at them and you'll see immediately, you'll just sort of see what needs to happen, and that's great. So for balancing equations, I'm going to show you like the long way of doing it with lots of steps, just to try and keep things really clear for anyone who needs that. But you don't have to show all of your work doing this. So if you kind of feel like you really get it and you want to just go ahead and do some practice, you can stop the video now and you can just go ahead and do more. But it's good to do a few more practice, and for those people who need a few more details on how to do it, that's what we're going to do. So I like to separate out, like I said before, my reactants and my products. So reactants are on the left, products are on the right. And I like to make a list, like we did before, of each element type. So I have potassium and chlorine in this reaction. And I like to make sure that regardless of the order that they're written in an equation, I always write them out in the same order on the products and the reactant sides, so that when I'm comparing them, I'm looking at the same number in the same place. So on our reactant side, we count out what we have. We have 1 chlorine so far, or 1 potassium, pardon me, and we have 2 chlorines. On this side, we have 1 potassium and 1 chlorine. I'm going to use a few different colors to do this, just to sort of try and make it as clear as I can. So I can see that the potassium is balanced already, but the chlorine is not. We have 2 on this side, we need 2 on that side. So we can do that by adding a 2 as a coefficient in front of the potassium chloride. That's going to change that to 2, but it's also going to change the potassium to 2. So now the chlorine is balanced, but the potassium is not. We have 2 and 1. So to balance that out, we can add another one over here by putting a 2 in front of the potassium there. That gives us 2 of those. So now that's all balanced and all done. So that was a pretty easy one. Let's try another one. Okay, this reaction has more pieces to it. So I have iron, I have nitrate, I have copper, and I have hydroxide. Now you see that we've got polyatomic ions here, so nitrate and hydroxide. But you'll notice that they're the same on both sides of the arrow. We have nitrate as a group again and hydroxide as a group again. So when you're balancing reactions with polyatomic ions, I would recommend that you keep your polyatomic ions as a group together. They kind of move as their own separate group, rather than splitting it up into nitrogen and oxygen and hydrogen, because that'll make it a lot more complicated for you. So I'm going to list my elements. So iron, nitrate as a group, copper, and hydroxide as a group, and then same order on the other side, regardless of the fact that it's not the same order that they appear in along the top. Okay, so iron and iron, and so on and so forth. Start by counting out what I already have. Here I have 1 iron, and I have 3 nitrate groups, so 3 times this whole grouping. I have 1 copper and 1 hydroxide. So that's my numbers on the reactant side. On the product side, I have, again, 1 iron. Here I only have 1 nitrate group. Copper I have 1, and hydroxide I have 3. So the 3 outside the brackets tells me I have 3 of that whole grouping. So I can see that my irons are balanced and my coppers are balanced, but the nitrate group is not and the hydroxide group is not. So for the nitrate group, I have 3 on this side. I'm going to need 3 on the other side. So I'm going to add a 3 there, which is going to change this from a 1 to a 3. And it's also going to change the copper from a 1 to a 3. So now iron is equal and nitrate is equal, but my copper and my hydroxide are not. But I can fix that because 3 here, I need 3 here. So I'm going to add a 3 as a coefficient in front of copper hydroxide, which will affect the copper, but it will also make my hydroxide 3. And when you're balancing and things kind of work out for the last thing like that, it's usually a good sign that you did it right. All right, I'm going to do one more. These types of reactions, where you have carbons and hydrogens reacting with oxygen, these are called combustion reactions, and we're going to get to the types of reactions soon, but they tend to be very challenging to balance. They can be harder than lots of other types. So we're going to, again, write out all of the elements in the same order. So carbon, hydrogen, and oxygen on both sides. We'll count out what we have at the beginning. So here we have carbon, we have 7. Hydrogen, we have 16. And oxygen, we have 2. On the other side, we have carbon. Hydrogen, we have 2. Oxygen, you have to be careful here because oxygen appears in both product compounds. You have to add them together. So there's 2 here plus 1 over there gives me a total of 3 oxygens on that side. And that can be where things kind of get tricky, is adding up when you have an element in multiple compounds. Okay, but we always want to balance oxygen last. So that's one of the little rules, is do oxygen last, do hydrogen second to last. And it'll generally help make your life a little bit easier. So carbon first, we have 7 on this side. We want 7 on the other side. So we need to put a 7 as a coefficient in front of this carbon dioxide. That's going to change carbon to 7, but it also affects the oxygen. So now we have 7 times 2 is 14. So we're at 14 plus 1. So we have a total of 15 oxygens on this side now. Next, we've got hydrogen. We have 16 on this side. Over here, this comes in pairs. So to get 16 out of pairs, we need to multiply it by 8. So 8 times 2 gives me 16. So now my carbons are balanced, my hydrogens are balanced, but this 8 also affects the number of oxygens. So we need to recount their number of oxygens again on the product side. So 7 times 2 is 14. That hasn't changed. Plus 8 times 1 is 8. 14 plus 8 is 22. 22 oxygens on this side. We need 22 oxygens on the other side. Oxygen comes in pairs, so 22 divided by 2 means I need 11 molecules of O2, and that will change that to a 22 and balance that one out. Okay, so there's a few practice questions. Hopefully you get the idea. Now, I'm going to quickly look at a couple examples where people have tried to do this incorrectly. So in example number 3, we have a skeleton equation here for nitrogen plus hydrogen makes NH3. So is the following equation balanced? If not, which elements are not balanced? So here, nitrogen, 2 atoms on this side, only 1 on that side. Hydrogen, 2 on this side, 3 on that side. So is it balanced? No. Which elements are not balanced? Neither element is balanced. So now let's take that equation. Neither element is balanced, but somebody tried to balance it by writing it out like this. Okay, so what's wrong with this equation? They've taken the N2 is the same, but the H2, they made it H3 to match the 3 on the other side. And here they made it N2 instead of just N to match the N2 over here. So they've changed the subscripts to reflect the same number of elements on both sides. So technically, yes, it's balanced in the fact that it has the equal numbers of atoms on both sides of the arrow. But the problem here is that it's no longer the same reaction. So not the same reaction. Okay, it's a completely different thing. So we can't kind of circle those. Okay, we cannot change the subscripts. So we can increase the number of molecules, okay, of whole molecules by adding coefficients, but we cannot add any subscripts or change any subscripts because that changes the actual molecule to being a different molecule. Okay, so we cannot do that. All right, so the next few pages you'll see are a whole bunch of equations for you to do some practice with. You'll see the line over here. Just ignore that for now. We're going to come back to these pages again when we do types of reactions in the next lesson. So really for now, all you're doing is balancing out the reaction. You don't have to rewrite it. You can do like I did before and do it sort of the long way and show all of your steps. Or if you want to just go ahead and put the numbers in, if you can kind of do it as a mental math exercise, then you're welcome to do that. You don't have to show all your work. The answers to all of these pages, so all of the balanced reaction equations, are in the folder of answers so that you can go back and check your work and see how it went. And if you have any questions, just let me know.